Okay, hello everyone. This is additional content for chapter 12, vectors. So this will be the introductions, and I hope you're already familiar with the vectors, and this is just a review on the vectors. So we are going to start with the 3D space, which we are going to see that we are going to observe the coordinates or anything happen in space, and we simply define the space in 3-dimension axis. So we have x, y, and z. Okay, and then we can also imagine that between these axes, okay, we have some planes that we call the xz, yz, and xy plane, like this picture here. That is it's like they are slicing the space, right? Okay, and also if we want to make a points at the coordinates, we can make the coordinates like this p. Okay, so it means that we move from the origin. Okay, so the origin is here, so we move from the origin a, because it's x-axis, and then y-axis b, like that, and then the z-axis c. Okay, and I think that's pretty much very intuitive, right? Okay, another things we can, based on this plane here, if we take the in R, this R cube means it's going to be in 3-dimension. Okay, if you have this R, this means it's 2-dimension. Okay, so in 3-dimension, if you have a line equation like z equal 3, which means that it will cut the point on this z equal 3. Okay, so we are going to have, like, it's actually like really large plane that is going to cut over z equal 3. For x and y, they are not limited. Okay, so because the only way we see this plane is just when this equal 3, so this is the plane. Okay, and then y equal 5, like this. Okay, so we are going to slice the plane. Okay, slice the space with plane y equal 5. Okay, all right. What else do we have? So if we are going to, for example, to make the xy becomes limited, let's say we are going to have x squared plus y squared equal 1, and then z equal 3. So which means we are going to have something that is cut z equal 3, but the limitations for xy is a circle with radius 1, like this picture. So this first picture here will show you that this is the circle. This is the circle which has the radius is 1 from the x squared plus y squared equal 1, right? Okay, now if we got x squared plus y squared equal 1 without any any limitation on z, which means that we are going to have the circle all over the place on z. Okay, so here, and then we combine all those circles, we kind of make something like this volumetric shape, right? With us like a cylinder. Okay. Okay. Now another thing in this introductions that I want to show you is we could have this distance. Okay, so of course if we are able to locate our points in this 3-dimensional system, then if we can, oh sorry, this is, it's got lost, I don't know why. So if we could locate within these two coordinates, then we can find the distance. Okay, how to find the distance? Basically basically, oh wait, this is not x2. So this is going to be x1, oh this is x2. So x1, y1, so let's say this is x2, this is x2, x2, this is also x2, and this is going to be x1. Okay. Yeah, so based on this triangle here, we're going to take the Pythagorean, and then we develop the distance formula, which is, let me just write the conclusions there. Okay, that's the distance formula in 3 dimensions. Okay, basically we are going to just take the differences between each axis, between the 2 coordinates, okay, between P1 and P2, right? And then we take the squared and then square root all the sum, right? Yeah, I think no big deal there. Okay, now the same the same approach, we are going to take this sphere, okay, with this x, y, z, and then HKL, this is the center, okay, the center of the sphere. So we can treat the center as in our origin, right? So basically, if we want to make this formulations, we could make this into our distance formula approach, and we can say that this is our sphere equation. So if we have the center HKL and we have the radius r between those two, between P and C, we could make this the distance equations, right? And then we could write down that if the center is in the origin, then we could just write this, okay, x squared plus y squared plus z squared equal r squared. Okay, I think that's it for the introductions. Okay, I will show you another sections, okay, later on. Okay, now let's continue on more geometric description on vectors. Okay, so if we imagine like a line with arrow and it has a value, let's say we take this as u, this is connecting point from A, let's say, to B. Now we can also write this as AB with that arrow on the top. That means that it's a vector of from A to B, right? Okay, so this is the initial point, we call the initial point. This is the terminal point, right? So vectors need to have direction and also magnitude. Okay, I think you can clearly imagine, because in physics you also describe vectors, right? You also need to learn on vectors, and you are also using vectors to at least to elaborate how the forces works, right? Okay. Okay, so we start with the vector addition. Okay. So the definition is, if we are going to add a vectors that has direction and also magnitude. Okay, for example, we have this u and v, right? So we want to add this to u plus v. So first, we can move around these vectors as long as we are not changing the directions, right? We can move that and move here, and then we simply make another path, right? we make a path that is start from here, goes here, and then goes there, and we can connect the first initial point here, go to the final point. Okay, so connecting this with that. Okay, and this will be our factor addition. Okay, so we call this the triangle law. We can also have another point of view, and we can make the, aside from this triangle law, and we can also have the parallelogram. Okay, idea is still the same, that the direction, this v, the same directions, right? This u also the same direction. We can move around these factors, okay, to build our factor additions, right? And also the factors we can multiply with a scalar. Okay, we can multiply with another constant, another magnitude. Okay, so we can multiply with the scalar multiplications. Okay, so if c is scalar and v is vector, then we can have a multiplication of scalar, which is cv, so vector whose length is c times of the original length v. Okay, so we can have like many possibility. So we start from the original v and then multiply by 2. It's twice of the original length, or half original length, or opposite. So we multiply with the negative value and it becomes the opposite directions, right? And so on and so forth. Okay, what's the deal? Okay, what's the deal? So we could say if we take u minus v, this means u plus the negative v. Okay, so which means we are going to, let's say this is our u and v, which means that we are going to make v in the opposite directions and then do the same thing. We're going to start from the initial point and end with the final point. Okay, so I think that is not really that complicated, I believe. So if we have let's say u over here, and let's say v is here, which means that this is going to be here. Now instead this v going there, we are going to take, let me take this size. Maybe make it another. So this will be minus v like that. You can make it here, or you can make minus v that like that also, the same conclusions. So this will be u minus v. Okay, all right, now next is we could have a components of a vector. For example, if we have a vector a that is a1, a2, a3, okay, which means that we are going to have three-dimension system. We are going to rewrite all this into the, or from the origin, let's from there. Let's say from here it's going to be having some coordinates, which is coordinates of a1, a2, a3, and we are going to have this line here is our vector a. Okay, So this is C, X, and Y. So we could make these points, okay, we could make these points as in, wait, here. So if we take the points A and B, with each coordinates x1, y1, z1, and x2, y2, z2, then we can represent factor AB with the difference between those 2 points, okay? Okay, and then another notes is we can have a magnitude, okay, or length. How to find the length is we are going to square root the vectors and then take the square, take the sum, take the square root, okay, for all the coordinates. Okay, that's the magnitude or length. And then we also we can add vectors algebraically. So if this is our 2-dimensional vectors, we are having the a plus b, okay, and then basically we are saying that we are going to add each axis, okay. So a plus b means that a1 plus b1 and then a2 plus b2, okay. And then if we look on more general view, we can have this, okay, for 2-dimension and 3-dimension. So we need to add each one of the coordinates. It means the axis, okay. Okay, you can pause the video if you want to take notes, okay. Okay, now we can also look at this if we multiply with the scalars, which means that we are going to see that the components also multiplied by the same constant, the same scalar, right? Okay, and then from those descriptions we can have this property of factors, okay. How do we add, how we are multiply this with a scalar, okay, how we are having some multiplications, and then how if we multiply with another constant or value, right? Okay, another point of view is the basis, okay, the basis. So this is what we call the standard basis vectors, okay. So which means that this is going to be for each x, y, and z, they are precisely at this value, okay, at this one value, one unit value. We call the I, j, and k. So we can rewrite the for example, if a is a1, a2, a3, we can write a as a1i plus a2j plus a3k, right? And then to end this these sections, let me write it more clear and clean. And to end this, one example is we call the unit vectors, okay. So what is unit vector? Unit vector is the vector that has length, the unit is 1, okay. So for instance, I, j, and k, they are all unit vectors because they are, its length is 1, right? 1 unit, okay. So one unit vector we can rewrite as, so the vector defined with its magnitude or its length. So we have this is the unit vector, so unit vector. Okay, now that's for the sections. We are going to continue in the next sections, so please stay tuned. Okay, now we are in the section of the dot product. Okay, so we first start with the definition. Okay, so the dot product. Okay, if we have a and b, two vectors with each coordinates, and if we say a dot b, so dot product is kind of type of multiplications, and when we multiply these two vectors, we are going to multiply each axis for each coordinates, that is a1 with b1, and then plus a2 and b2, and then plus a3 and b3, and that's the dot product. Okay, now from from this multiplications, we can have some sort of, we call the property of the dot product, that we can see. And I think if you have time, you can also try to check and maybe trying to prove whether this is true or not. And of course this is true, but you can confirm how we get this proof. Okay, and another thing in dot product that is important is, let's see, if we have this a b, okay, this vector a, vector b, which means that vector a is from origin to a, from the point a, and b is from origin to point b. Okay, and then we have this side here we define as a minus b, right? So we have like a triangle, right? Triangular, so the vectors kind of make a triangle. Okay, now if we apply the, let me make it small, law of cosine, and we take the ab squared, so ab squared is here, which means that we are going to plus this squared and minus the two OA and OB, right? And then cosine the theta, okay? Cosine, that is the angle that is in front of the AB, right? That's cosine based on this triangle. Okay, now we are going to see that the AB squared is actually our vectors A minus vectors B and a squared, and then this is A squared plus B squared. Okay, and then we have this a squared, b squared, and then we have this 2ab. We can say, if we remember, okay, this one here, that if we have the a dot a, this is the a squared. Okay, so basically we can write that a minus b squared is a dot b, and a, oh sorry, not dot b, it's minus b dot a minus b. Okay, and then we can multiply this dot product. So a dot a minus dot b minus b dot a, and then minus become plus b dot b. So we can have a squared plus b squared minus 2ab, right? Okay. So this part here is going to be on the left side, so we can rewrite. Let me use the blue color. So a squared plus b squared or we can write this, sorry, we can write this 2ab, sorry. And then this will be a dot b. Okay, and then equal this a squared plus okay, and then minus 2ab is equal, so this would be cancelled all so this is negative 2a, and cancel this negative 2, so a dot b is equal, okay, so we can simply say from the dot product here, if we have this angle theta between the vectors a and b, then we can rewrite a dot b as the magnitude a, magnitude b, cosine theta. Okay, and also we can just write down the cos theta is a dot b divided with magnitude a, magnitude b. Okay, and then from this particular property, we could also write the conclusion that if the factors a and b are orthogonal, then a dot b will be 0. So they can be orthogonal if the a dot b is equal to 0. Okay, now I think one last thing before we end this dot product. We have this so-called we call this a direction angle and direction cosine. So this is direction angles and direction cosine. Okay, now if we take the angle, for example, the angle alpha, if we see this picture here, alpha is here, right? So alpha is between a1 and the factor a, right? So if we change this a1 into basis factor I, because in the x-axis, so the cosine alpha becomes a dot I, and then magnitude of a and magnitude of I, or this is going to be a1 over a. Okay, the factor a multiply with the basis factor multiply with the basis factor I, so it become a1 and then with the same method we can get the beta and also gamma. Okay, now we can see that if we square this cosine, okay? And then if we take A as these factors and we write down within the cosine alpha, beta, and gamma, so we can write this and we can factorize A and we can just write down the cosine. And therefore we could write A over magnitude of A equal cosine alpha, cosine beta, and cosine gamma. Okay. And this is what we call the direction of cosine. Direction cosines. And this is direction angle. Okay. All right. Now the last sections. Oh, I forgot the last sections that is going to be in this dot product will be the projections. Okay. Okay, so based on what we have in the A dot B, okay, we can write A B cosine theta. Okay. Now we could write B cosine theta as A dot B divided by A. Okay. Or we can see that this is the unit vector, right? Okay. So we could summarize this idea on these projections. We could make this within the two approach. Okay. The first one we call the scalar projections. Let me write first what's the idea first. So scalar projections of B onto A. Okay. So which means that this is going to be, I think, let me write this first here. Okay, this is the scalar projections. So projection of B, let's say this is B. So this is B, okay, this is A. So we project this B, goes there. So we are going to have this component B onto A. So this is read as component B onto A, right? But we are going to focus only on these scalar sides. Okay, so we can make this B as a scalar, and then that is the scalar projections. Okay, so this B cosine theta is the scalar projections. So we can say that this is the same with this. Okay. Oh, this need to have value. Sorry. So B cosine theta, right? Now the difference between the scalar projection and the vector projections, in vector we are going to make the vector still as a vector, not in the scalar. Okay, so we could have these two kind of projections. For example, let's say we start from this first. Okay, this means projection vector B onto vector A. Okay, so this will be B is projected here, and this will be the length. It's become a new vector, okay, or a new point, okay? a new point. So it's become a vector PS. Okay, so the beginning is vector PQ. Now it's vector PS. And now we can make this into this. So the difference, so actually the same, this part is the same, right? But we need to multiply with the unit vector, okay? With the unit vector A. So we need to multiply again with the unit vector. So this is unit vector, right? Or we can simplify this unit vector. So we could take this A dot B over the magnitude A squared and then multiply with vector A. I think you could just skip from this one first. I think it's easy to remember. You just need to multiply with the unit vector A. Okay. We can also have this. This is also the same projection of B onto A, right? But now it's going to that sides, okay, the other side, the opposite sides, okay. So that's it, the dot prac. We are going to continue and stay tuned on this additional content. Okay, let's continue. This section is about the cross product. Okay, so cross product. Okay, what is the cross product? How does it come from, and how we define this? Okay, so before we go into the what is actually the cross product, so it's actually another type of multiplication for vectors, which the difference between the dot and cross, if you see from the symbols, the cross has this like x like that multiply, and you have this process. So a2b3 minus a3b2 and so on and so forth. Okay, and how does we write this? We are going to see later. We need to incorporate the matrix to see how we get this result here. Okay. So let me start first with the reason why the cross product becomes important. Okay, so suppose that we have A, vector A. Let's say A is having A1, A2, and A3, and we have B that is B1, B2, and B3, right? And then we want to finding vector C, that is, suppose that this is C1, C2, C3, that is perpendicular to both vector A and vector B. Okay, so the idea is we need to make this C that is perpendicular directly to A and also B. Okay, so based on what we have before, that is when this perpendicular, so we need to make sure that A dot C is 0, okay, and also A dot B also 0, right? Okay, so we can write down A1, C1. Let me write just without arrow, okay, to make it more simplified. Plus A2, C2 plus A3, C3 equals 0, right? And then B1, sorry, why I'm writing this? Why? This is supposed to be B and C. Okay, B1, C1, B2, C2, B3, C3. This is also equals 0. Okay, so I think we can eliminate the suppose that we are going to eliminate the C3. Okay, so we are going to take this subtraction, but we need to multiply this with B, B3, and this is A3 to make sure that it's going to eliminate. So we eliminate, and then the rest will be A1, C1, and B1, C1. That's for C1. So we are going to have A1, B3, right? A1, B3 minus A3, B1. This is for C1, right? and then plus A2B3 minus A3B2. This is C2. This is equal to 0. And we get the result from this linear equations that C1 is A2B3 minus A3B2 and C2 is A1B3 minus A3B1. Okay. Now based on with this, then we can simplify and using this statement and giving back to this to find the C3, and we find C3 is actually equal to A1B2 minus A2B1. So we can write down C1, C2, C3 in terms of vector is A2B3 minus A3B2, A1B3 minus A3B1, and A1B2 minus A2B1. Okay. Now this is already, we have this similar result, right? So that is what we call the cross product. Okay, we call the cross product. So we say that this will be the cross product of A and B. Okay. Now to make this calculation in terms of this all A, B, C, the factors, I think we can make the calculation more simplified using vectors, or maybe more easy to process using vectors. So to start with, we can start with determinants. Okay, so in vectors or in matrix, if we have 2 by 2 matrix, we have the determinants that is defined by this. If we have this 2 by 2, this is going to be AD minus BC, right? And then let me make it a new page. So if we have the 3 by 3, so let's say A1, A2, A3, B1, B2, B3, C1, C2, C3. Okay, determinant is how to make this. So first, we are going to see this row, the first column and the first row. Okay. So let's say we cover this two, and we write the A1 here as our first component, and then the other component will be the determinant of B2, B3, C2, C3. Okay, and then we need to multiply with the covector. If you remember the matrix, what is the covector? Covector is simply, we say this is positive, negative, positive, negative, positive, negative, positive, negative, positive. Okay, so A1 positive, it's true, right? And then the second part, we take the A2 here. So we cover this part and this part. Okay, so minus A2, and then this will be B1, B3, C1, C3, and then plus A3. A3 is B1, B2, C1, C2. And then this will result in we could see the same result if A1 is I, A2 is J, and A3 is K. We are going to see that A cross B is going to be or let let me write first the 3 by 3. Maybe this is I, J, K, and this is A1, A2, A3, sorry. This is B1, B2, B3. And simply this is going to be the A2, A3, B2, B3. This is for the first component for I, and then minus for J is A1, A3, B1, B3. And then plus A1, A2, B1, B2 for K. Okay, now we can also make through the this B1, B2, B3, C1, C2, C3. Okay, like for example, if we take B1, so the first one will be negative B1, and we are going to cover this part. Okay, so we are going to have A1, A3, C1, C3. Oh, sorry. This is A2, C2. And then plus B2. B2 is A1, C1, A3, C3. And then minus B3 is A1, A2, C1, C2. And the result should be the same. Okay, so you can choose this part or this one, or if you want to choose C1, that's C1, C2, C3, it's also okay. It will be the same result. Okay, back to the matrix and the determinants. So this is how we are going to take the cross product usually. Okay, but anyway, I have my suggestions. Okay, so if you want to take this cross product like that, my usually way or calculations, we can take this, right? This is determinants, and then write another I and J, and then this will be writing another A1, A2, B1, B2. Okay, now next thing is we are going to multiply this and then sum all the subject all together. So A2 B3I plus A3 B1J plus A1 B2K. Okay, and then it need to be minus, okay, minus, and then plus again, but the other side of the arrow. Okay, so A2 B1K plus A3 B2I plus A1 B3J. So we multiply all together and then we subtract both sides. A2 B3 minus A3 B2 this is for I, and then plus A3 B1, right? A3 B1 minus A1 B3 J okay, and then plus a1 b2 minus a2 b1. Okay, I think this will be get the correct result, right? This is, we say, the same A cross B, right? Same A cross B, right? I think I made a mistake here. Sorry. Need to multiply with the positive. So this will be a3 b1 and then minus a1 b3. I forgot to multiply with the negative here, so that's why it's become a little bit different. But the rest is the same. Okay, so that's it. The cross product. Okay. So we can have the cross product using the matrices, and we could compute using matrix. Okay. And then we could take the this cross product using our right hand rule. So the thumbs will be the cross. Okay, so our index finger and the other fingers will be the vectors a and b. So a and then cross b. We could see like a screw. If you can imagine a screw, if you rotate screw from the left to the right, it's going to up, right? Upper directions, right? Okay, so you could also think like that. And also the this is conclusions, and then we also have this conclusions, the AB sine theta. But I think we need some theorem that supports this the angle. Okay, so I think, let me write. Okay, let me check. Okay, before this, we could also prove this part here using the A cross B and then dot A. Okay. Now you could try to prove this, and this will result in 0, and that's why it's orthogonal. Okay. Or you could also try the other that is also 0. So that would be orthogonal, okay, by the definition of the dot product, right? Okay. Okay, so this theorem can be proven through this calculations here. So we can start the calculations through the A cross B, and then we squared. So all the things inside is going to be squared. Okay, so this having a really long equations. Okay? And then we simplified, factorize this, some algebra, and I think this is quite advanced algebra. And then we get this conclusions, and this is basically we can relate to the dot product, right? And we have this 1 minus cosine squared and becomes sine squared. And that's why we get the sine theta from the sine squared and then take the square root. and this is equal sign, not the negative sign, because we are dealing with the positive sign. Okay. Another thing in this cross product is the parallel. So the vector A and vector B is parallel if their cross will be 0. Okay. Which means that the parallel, so A and B parallel if the theta is 0 or pi, right? So either way, the cross need to be 0, and therefore the cross here is 0. Okay. Okay. And then we can also, by this approach, this B sine theta, if we want to take the area of the parallelogram, we could take the area as A and then multiply with the B sine theta. And this is equal to the cross, right? So the cross product is equal to the area of the parallelogram of the vector A and B. Okay. And then with the cross product, we can also define the basis vector. So we could define the basis vector. So we could multiply with each other and we can determine the result. Okay. So the I cross J. So how to determine this? If we suddenly forget, we could just draw the 3D space. So let's say this is I, right? This is K. This is J. Okay. Okay, we start from, let's say, I cross J. Of course, this is going from the left to the right. It's going to up, right? Upper directions. If we take the J cross I, it's going from the right to the left. It's going to down, right? So it's negative K going down like that. If we take, for example, K cross J, so it's going from the left to the right, right? Left to the right, so it's going to be going there, right? So you can take with your right hand rules, okay? Right hand rules. And then we could also, using the other example as well. So let's say I cross K. So from left to right, it's going to screw to the left, right? So negative J. So you can imagine a screw. Okay. Okay, some property on this cross product is we have all this. So of course, the A cross B is not equal B cross A, but it's equal to negative B cross A, okay? Because of the directions, okay? The direction to make the cross product is the perpendicular to A and B, right? Okay, lastly, we can have this, we call this is the parallel pipe, and how the best way to get this is, if we get A, B, C, right, and we have the angle theta, okay, defined between this B cross C and A. And if we want to make the approach for the volume, so the area multiplied with height, right? So the area itself, the area of parallelogram is with BC as the parallelogram is B cross C, right? And the height is, remember the projections, A to the B cross C to this height will be A and then cosine theta. And this simply related to the dot product, right? To the dot product. So we could take this A dot B cross C and then magnitude. Okay. So this will be the volume of parallel path. Okay. And I think that's it for the cross product. Okay.